One of the prospective areas in AI is integration of efficient neural network methods in uncertainty. Our next speakers are going to tell us more about it. Please welcome leading employee of AIRI, Aleksandr Panov and Alexey Skrynnik. Yes, hello everyone. My name is Aleksandr. Together with my colleague Alexey, I will tell you more about a very interesting task, neural-symbolic integration. We're going to show two examples how it can work in scene representation and one other example. This is a brief plan of what we're going to talk about. Briefly, let me tell you about the problem, about how we can solve it, and what is our original methods of vectors to describe structured scenes that improves the results and helps localization. It's important in robotics. And Alexey is gonna talk you through another example in multi-agent reinforcement learning. It sounds quite scary, neural-symbolic integration, but by the name you can tell that we wanted to integrate very popular neural network methods that are great at recognition, and overall they're great at working with raw data, particularly with images. And we wanted to integrate them with traditional methods, with conventional methods that had been developed before the neural network methods, with a symbol AI that has this symbolic approach. And there are two subtasks here. It's reflection. This is what we're going to talk about, and planning. Behavior planning. On the right-hand side, there are two well-known examples. I'm sure you have recognized Boston Dynamics robot. Neural-symbolic integration is not required there. It's a great example of robotic simple robots are dancing and they are doing some acrobatics and they don't need any training. And on the picture on the right, there is another robot. It's a human-oriented environment robot application in Korea and in Asia. Those cafes and restaurants where there's a trolley, a robot taking your order, it's gaining more popularity. It's quite primitive, but we would really like to automate the waiter function. In this case, we need to integrate what the waiter sees with his sensors. So we need to integrate experience of a waiter. He needs to understand what's in front of him, a person or an object, and integrate it with what is told to him by people using language, naturally. And this integration of symbols and information from sensors must be efficient and must help predict some behavior and model some behavior, and also to understand what's going on around using sensors. This task comes from a well-known AI problem of symbol orientation. There is a picture in the bottom. When we use a concept, and this concept can be described with an image, on the other hand, it is a symbol. This concept has certain properties that we can use in planning. In order to combine this percept with symbol, this is a very non-trivial task, and it hasn't been resolved in our AI yet. This slide shows two examples of how these two worlds can be integrated with each other, symbol world and neural world. One of the approaches is structured embeddings. Embeddings are vectors, vector understandings, and they are a way out of intermediate neural network structures. So we can use vectors to make sure that vectors are useful. They have useful features similar to symbols. Second option is neural network approximations in NetHive traditional conventional search, which is the core of planning. On the right, on the slide, you can see an example of how we can use a search on a graph, and the state of graph is predicted with the help proof of approximators. This is the task that is used in the example of Alexey. It's going to be used widely. And I will make a very simple example of robot localization, how to use special embeddings that can be developed prematurely, or we can take an intermediate product of neural networks, and we can do some operations to these neural networks, to these embeddings. So what are the things that we're going to need and in order to add more features, more properties to embeddings? The source is in vector-symbolic architectures. As I said, there is a symbolic approach, and the main idea here is that we can interpret them specifically. We don't have any other way. One symbol is separate from another. They're antagonal to each other, and some symbols are more similar to each other, and we can train them, we can teach them, we can fine-tune them. So let's try to bring them together. Let's try to say that we have antagonal vectors that can be adjusted or trained along the way in the process when fine-tuning the neural networks. Let's see where it might be applicable and what are the tasks that we can resolve. Place recognition task. It's very important in robotics, particularly when we want to orient inside the room. Let's imagine that we have a waiter robot or another robot, and he sees these 4 pictures. You can see them yourself. We can add more additional sensors to the robot, but let's imagine that by the picture we must understand whether I'm in the same location or not. You understand that we can rotate, we can change the angle of view, we can have a look at a different height, and we're in the same spot. So it's a task of comparison of images. Picture on the left is very similar to the picture on the right. The robot is located particularly almost at the same place, and here place recognition is solved the same way. But when we compare the first and the second, we understand that we're in different locations, and comparison of pictures is a non-trivial task. We must have additional information about location of objects, that they are not matched and that they are not the same. And in order to resolve this task, our team has created an additional data set that is called H-point log. We split it into 3 parts, to 2 parts, simple and complex. On the left, on the images, you can see the realistic habitat where the points were located. We had our angels there. We would rotate it by a little bit, and we would make images and to confirm that he's in the same spot, but it's a different angle of view. And thus, we collected a huge data set to resolve exactly these tasks, to localize inside premises. So these are realistic images because the simulator developed by Facebook allows really to make it realistic. A huge volume. In the case that is on the right, when we are next to the wall, we don't have a lot of elements around us, and the wall is blocking the view, and we can't see whether it's the wall in a corridor or in a room. Naturally, these are more complex cases. We need to be able to tell small details apart from each other, and we need to also know whether these details are the same in different parts of the image. Okay, so what can we do here? We train the neural network architecture. We resolve the task of similarity, for instance, but actually it turns out that these classical architectures can be improved. Let's imagine that we have a large size vector. The size is 10,000, and let be elements 0s and 1s. Before 1s, there might be fewer 0s. And it turns out that it's very convenient to work with these vectors. It's great to do deductions and additions. And then we can deduct these vectors from one sole vector in the end. It happens so that we put words together without ruining the structure of words, and the sentence is the same vector, but it has more ones in it. This is a very useful property of symbols that we have transferred into vectors. Let's see how it can help us. On the left, there is a scheme. With the help of these operations of adding and deductions, we can code this simple scene. We have coordinates x0, x1, and there is a triangle at the bottom and circle on top. We have elements that define different different types. We can deduct it backwards later, but with a small noise. And then let's have a look how we describe the scene this way. We're coding the depth, we're coding the type of the object. We can type different additional traits, for instance, color or shape. And we can describe the image and we can add it to vector description of the stage that is done by a neural network. This is an example of the network that we developed with our team. We decided to create a traditional neural network method that was done. It is doing traditional embedding, and we added our vector that is large size vector. We fused these two vectors, we merged them together, and we receive one solution. And we see either we're in the same spot or not. This is how TSV log can resolve different other tasks, even when they're more complex tasks. In red, you can see the right answers, and here are quantitative metrics. In this task, in complex data sets, we are better than the other results, and it's better. Previously, the difference between options was like 1 decimal point, and here it's much more significant. Here is some literature that you can look into. These are traditional classic methods, symbol methods with the help of VCA, and I'm going to hand over to Alexey now. He is going to tell you about the second option that can be used for the other example, the other case. Thank you, Aleksandr. Let me tell you about another neural-symbol integration, and we're going to talk about the task that is called multi-agent planning or pathfinding. What does it mean? What kind of task is this? It's a problem when we have a lot of different robots or a lot of agents, and they have some targets, and they must reach those targets or these destinations that they have. But they might interfere with each other, and they might have different other barriers on their way, and there might be some other dynamic objects there. On this video, you can see how one of warehouses work. It's managed centralized. The management is centralized. There are a lot of robots at the warehouse, and they're sorting some things for sales, which accelerates sorting of products, and it doesn't require any human resources here, which is good. Typical application you can see on this slide, and we can move on. What we are doing, and what I wanted to tell you about, is a problem that when we use centralized algorithm, when there is full understanding of the environment, it's a rare case, and it limits the amount of application of this approach. This slide shows some examples where agent doesn't have a full understanding of the environment. So the environment is partially observed, and the agent can see just a few cells around him, not all the environment. On A example, on A picture with errors, you can see how agent is getting to his destination, and on the first picture, it's the most simple case. The agent can see all the barriers, and he can plan his path and reach destination. In the second picture, it's a little bit more complicated. The agent doesn't see his destination, but if he moves in that direction, he will notice it and will reach destination as well. The third case, when agent needs to go around some other barriers, and you can see I could not go along the shortest path, so I had to find some bypasses to reach the destination, to reach the goal. This option, when we have just one agent, is easily resolved with traditional planning methods, with Dester-Light algorithm, when we know the destination coordinates, or with not the classical, but with reinforced learning. Second case is a little bit more complicated when we have two agents in the picture. Also, partial observation, decentralized environment, agents are not communicating with each other. On the first picture, everything is quite clear and simple. Agents start moving towards their goals. And on B picture, they can see each other. This is where we have the difficulty. The point where they have to resolve their conflict. What's their conflict? That they meet in a narrow corridor and one of the agents needs to let go the other one first. In this case, it happens quite nice. The blue agent lets the red one go, and both of them reach their destination successfully. These tasks can be resolved with a multi-agent reinforced learning. We are proposing to apply it in one more agent. We use it in Monte Carlo tree search. Let me tell you about Monte Carlo tree search approach. The main idea in Monte Carlo tree search is, well, let's take the most basic case of this approach, where most often we use Monte Carlo tree search. AlphaZero algorithm and board games, for instance, chess. Let's have a look at chess. The idea is that we play against a competitor and we want to make a better move. In order to do that, we build a tree. The top of every tree meets the situation on the board. Every top also has its value, how valuable it is to us. So the task is to build such a tree so that we could choose a better move. This tree can be built in 4 stages. Stage 1, we choose the summit, we choose the top. That will help us expand. So first stage is selection, then expansion stage. Out of selection, we choose one action, one move. Then we simulate this move. And the 4th stage, when we have done simulation and we have reached the value, then it's a backward movement of this value along the path that we took on the way to the goal. The strategy that is used in this simulation might be random. Sometimes we might use random strategy and gain the result anyway. In our case, in AlphaZero, we have a neural network that predicts this value or approximates this value. This slide shows the scheme of our approach for a multi-agent planning. In order to resolve these tasks, we split the main architecture into 2 modules. The first module is responsible for reaching the goal, and we have used quite a popular algorithm, proximal policy optimization. This is multi-agent reinforcement with learning. And the second module is conflict resolution. And here we apply Monte Carlo tree search. In this article, we used a simple option of combination of these 2 modules. Every network would predict a certain distribution of actions, then we would mix these actions and we would receive the best solution. You can look at it at the table. On the right, you can see, and on the right in bold, you can see the best results of this hybrid strategy. And on the left, you can see results separate, first in the model of conflict resolution and in the second, goal reaching. As an alternative to Monte Carlo tree search, we used Kumik's algorithm. It's quite well known. So here are the results, and this slide shows additional information in case if you want to learn more about this issue. And that's it from me. Thank you very much for your attention. Thank you very much, colleagues. It was a great presentation. Unfortunately, we don't have questions. Obviously, it was very straightforward and clear.